Okie dokie smoky. Today we are going to finish up 1.10. Okay? 1.10, rational functions and vertical asymptotes and x-intercepts and all that stuff. Here's just another example of where we left off yesterday. What we have is another function, and we see that the limit as x approaches -1 from the left is equal to the limit as x approaches -1 from the right. They're both 2. Because my graph approaches the same y value from the left and the right, from this x, what do we know should be there? If you approach the same y value, that means that the graph is pointing to the same point, a hole in the graph. The only other time where this happens, where they approaching an x value, you come to the same y value, other than a hole in the graph, is an actual coordinate of the graph. It's the only other time that occurs, where the left and right hand side say the same y value. So for this question, we are going to make the assumption that this is a hole in the graph and not just some random coordinate of the graph. There's a hole at -1, comma, +2. Yes? And down here, we have approaching the value x equals 3 from the left, approaching the value x equals 3 from the right, both shooting to an infinity. When your graph heads to an infinity, when you approach an x value, what does it tell you about that x value? Lots of people, come on. Asymptote. Yes, thank you, gentlemen. Yes. Good thing Cooper's here. So yes, it's an asymptote. A vertical asymptote. At x equals 3. So we're going to write kind of small. Now look, because we can't see a graph, we have no idea what the horizontal asymptote is, then we are going to assume that the horizontal asymptote is the x-axis because that's the easiest thing to do, which is basically what I was discussing with you before we started the notes. Okay, so because there's no picture, we can say the y or the horizontal asymptote is whatever we want. So we'll say y equals 0. We'll say the x-axis, meaning this graph will not touch the x-axis, so there will not be another factor in our numerator. There'll be a single factor in the numerator like we did here. This one's g of x. We'll say that there's some kind of vertical stretch or shrink and possibly reflection going on. And we'll say that because there's a hole at x equals -1, I know that x plus 1 is a factor of the numerator and the denominator. Because remember, holes happen when we cancel an x off of a function. But because there's a vertical asymptote at x equals 3, I know 3 is a 0 of the denominator even after all the canceling. So there's an x minus 3 hanging out in this denominator. Just like yesterday, in order to figure out what that a value is, you simplify the function. We see that it simplifies to a over x minus 3. So essentially it tells us this. Y equals a over x minus 3. That's what it'll simplify to. You could then use the coordinates of the hole as the x and the y to plug in for here and here to solve for a. Y is 2. A is -1. -1 minus 3 is -4. Multiply both sides of this by -4, and you will get that a equals -8. Because the bottom of this fraction is -4, you just multiply both sides by -4 and you get a equals -8. And like I said, we're going to assume that there is no x-intercept. We're going to assume that the x-axis is the horizontal asymptote. So we'll say a possible answer is g of x equals -8 times x plus 1 all over x plus 1 times x minus 3. Do you have any questions about building a rational function from limit notation? So you know how to use limit notation to identify a hole in the graph and identify an asymptote. Yes, ma'am. A vertical asymptote.
So if I plug in that equation into Desmos, would Desmos show the hole in the graph?
So Desmos won't show you a hole in the graph, but if you click on the curve itself and then drag, it'll show you coordinates. If you go to this coordinate, it'll say undefined. But it won't just put a hole in the graph. So anytime you see a picture that looks like it came from Desmos, especially if I produced it with a hole in it, what that means is I put a coordinate there and told it make that coordinate open. But no, Desmos won't automatically show you those things. I don't know why. You'd think it would, but it doesn't, unfortunately. Yeah.
I don't have a specific question.
Okay.
But I'm just a little confused on the whole thing.
No specific question, just a little confused on the whole thing.
Yeah, like I got this is gonna
Hold on, how about this? Let me ask a few questions. Do you know why this is true? Okay, and that's what. So this is specific. Do you see there's a hole in this graph here?
Yep.
Do you notice that as I come from the left side and I come from the right side, both these arrows are pointing at this dot? It's open, but you get it.
Yep.
So can we agree then that on the left of this hole and on the right of this hole, the graph is attempting to get to this y value? Okay. Well, that's what, where is it? That's what that looks like. To the left of x equals 3 and to the right of x equals 3, we're attempting to get to this y value of 4.
What's the little signs above the number?
The minus sign means left of and the plus sign means right of.
So x is going to the left.
No, this is x is going to 3, but from the left side, that's this arrow. This is x is going to 3, but from the right side, that's this arrow.
Okay.
But notice they're going to the same y value. That's the dead giveaway that you're pointing at a hole in the graph. Or you're pointing at an actual coordinate of the graph. Okay? So here then, what we did was we said, because to the left of -1 and to the right of -1, we're both pointing at this y value, we're making the assumption that there is a hole at this x comma this y.
Okay.
Okay. Here, do you know why this is a truth?
X equals 30.
Yeah, do you know why that's true based on this?
Because I'm gonna make a guess. And say
Don't make a guess. The answer is yes or no.
no.
No. Okay, so we come back to our picture. On the left side of this red dotted line, do you see that as I get closer and closer and closer, this goes further and further down? This is approaching negative infinity on the left.
Yeah.
This is approaching positive infinity on the right. At all vertical asymptotes, graphs will go to an infinity, always. So because as I head towards this x, I'm approaching an infinity, I know there's a vertical asymptote at that x. It didn't even need to be on both sides. It only needed to be on one side. If the graph approaches an infinity at a specific x value, you have identified a vertical asymptote. Okay, next. Do you understand why this is in the bottom of the fraction in red? Vertical asymptotes always occur when you attempt to divide by 0 in the simplified version. So if I simplify, the x plus 1's cancel out, correct? If I plug in a 3 right here, I'm trying to divide by 0. See it? 3 minus 3 is 0. So since I knew that 3 was a no-no, I know that x minus 3 had to be in the bottom.
Okay.
Now because there's a hole at x equals -1, there's an x plus 1 down here because I also couldn't divide by 0. Oh, but it would have canceled out. So since I had to write it here, I had to write it there also. Because that creates a hole when those x's cancel. And I tried to color code it. This green stuff is why this green is here. This red is why this red is here. And from there, we go, the only other information I have is that at this x, my graph wants to be that y. So I said there must be some multiplier here more than likely. We simplified, and we crossed out the x plus 1s, and it says there, our graph is essentially y equals a over x minus 3. Take this x, y, plug them in here. This is how we solved for a. Boom. That's the whole shebang. Okay? Mm-hmm. All right. We have a picture. We have an equation. What we're going to do is we're just going to analyze. We're just going to say things we know to be true just because we're looking at this picture and this equation. Cool? First of all, this would simplify. There's an x minus 3 in both the top and the bottom. So they'll cancel each other out. The simplified form is f of x equals 3x plus 1 over x plus 3. Now we know that x can't be positive 3, but this at least is what it would simplify to. Because the x minus 3's would have canceled. The whole. Did it land at a pretty point? A perfect grid intersection? No, it didn't. But you can see the x value for that hole. You can see that the x value is positive 3. And we knew that anyway because 3 makes this and this equals 0, but those would have canceled out. That's what creates the hole. So we know our hole happens at 3 comma. And if we know the x value, in order to find the y value, all you do is plug in 3. Where? Well, I can tell you not here. Because if you try to plug it in here, you're going to do 0 divided by 0, and that's big no-no in mathematics. So where do you plug in 3? Here. You plug it into the simplified form. You see, the simplified form doesn't have a problem with x equals 3. It has a problem with x equals negative 3. No issues with positive 3. So you plug in positive 3 to this. So the y value would have been 3 times 3 plus 1 over 3 plus 3. That is 10 over 6, which reduces to 5 over 3. The domain of this graph is just all the x's where you're allowed to exist. The graph is not allowed to exist at this x or this x. So hopefully you can see there's 1, 2, 3 zones where the graph exists. We're just going to describe those 3 zones and string them together with unions. This zone is to the left of negative 3. This zone is between negative 3 and positive 3. And the last zone is to the right of positive 3. For the range, we're once again just looking at the picture. And we're hopefully seeing that this graph exists at every single y value except for the y value of the whole, which was 5/3, and the y value of the horizontal asymptote, this one doesn't cross it, which is 3. But it is still 3 zones, and we'll string those 3 zones together with unions. So below 5/3, between 5/3 and the horizontal asymptote at y equals 3, and then to the north of the horizontal asymptote of y equals 3. So from 3 to infinity. That was these 3 zones. So what we're going to do is we're going to pretend that this is a free response portion of a test. And it says, find the vertical asymptote. What would we say is the vertical asymptote? Cooper? X equals negative 3. Cooper, question for you. Could you just say negative 3? Why not? Why can't you just say negative 3? because it could have been horizontal or vertical. Correct. This is a vertical asymptote. All vertical lines are x equals a number, so you must say x equals to get that credit. Same logic for y. I have to say y equals for the horizontal asymptote. And you can just see it on the picture. It's at y equals 3. Yes, sir. What's up? Oh, you were going to volunteer?
Yeah.
Oh, I'm sorry. I'm sorry. So you can see that y equals 3 on the picture. And you know, you didn't need the picture to know that, because look at the degree of the top and bottom. It's going to be quadratic over quadratic. So as the degree of the top and bottom are equal, that means it was going to be y equals leading coefficient of 3 over leading coefficient of 1. Y equals 3 over 1. When limits say to the negative infinity and the positive infinity, this is end behavior. But what is the end behavior of our graph? What's it become to the far reaches of the infinities? 3. It approaches the horizontal asymptote. That's the definition of a horizontal asymptote. It's if the end behavior is a number. If the end behavior is a number, horizontal asymptote. That's how you know it, just by using limit notation. You go, ooh, there must have been a horizontal asymptote there. Now it says go to the left of negative 3. So I'm going to go to the left of negative 3. That is over here. And my graph is pointing up. So what's the limit? What's the y value trying to get to as I get closer and closer and closer to this value for x? Well, x is trying to get to negative 3. There you go. So we're shooting up to positive infinity. So when you say the limit of f of x, what you're saying is the goal of the y value. At this x, what is the goal of the y value? That's what this says. So if you're to the right of negative 3, the goal of your y values is negative infinity, he whispers. Absolutely, negative infinity. Good. And what is going on at x equals positive 3 in our picture? There's a hole in the graph. That means the graph has the exact same left limit as it does right limit. They're pointing at the same y value. It's the y value of the hole, 5/3. I do want to add one more thing to this page. And I'm going to do it in the space that's below the equation. Okay? And I'm going to do some quick maths while I pause the video. Okay, so quick maths are done. Now I got to ask you a question. Does this graph have any issues with any other x's other than x equals negative 3 and x equals positive 3? No, it doesn't. It has basically what you would consider a closed dot everywhere else, right? Anywhere a graph is drawn is considered a closed dot. So what if I wrote this? This says, what is the goal of the y values as x gets closer to negative 7? Does my graph have a problem with x equals negative 7? No, it does not. So what do you think we do to find the limit of the y value? You go to where the point is. You literally just plug in negative 7. So you either plug it into an equation or you look at the stinking picture. Now if you plug it into the equation, you'll get negative, and this is when I pause the video, you'll get negative 20 times negative 10. That's positive 200. And on the bottom, you'll get negative 16. So 200 over negative 16. And I don't expect you to know what that is, but if you just go here and you go to negative 7 and you track it up, you can see the answer is 5. That, what I just said doesn't make any sense, does it? It can't be 200. Negative 21 plus 1 is negative 20. Negative 20 minus times negative 10 is 200. Something's not working here. Oh, because it's not 16. This is negative 10, and there you go. It's over negative 40. So anyway, the answer is positive 5. I could do basic math. Essentially, if it says limit as x approaches a number, and that number's not an issue, there's not a domain problem there, then you just plug it in. That's what this says. This says, well, whatever the y value is when x is negative 7. See, I couldn't do this for the numbers negative 3 or positive 3 because my graph didn't exist there. Yeah?
If you thought there was a hole there, though, and solved for one,
So, and that's why I was saying, let's say there was no picture and there was nothing like this. If I just say the limit as x approaches negative 7 of f of x is 5, then that tells you the coordinate negative 7 comma 5 is on the graph. Now, if I say the limit as x approaches negative 7 from the left is 5, and the limit as x approaches negative 7 from the right is 5, and I don't tell you anything else, there could be a hole there. Or it could just be an actual dot on the graph. And that's why I said for this example, we're going to assume that there's a hole there because otherwise we're kind of wasting our time. But because we can see the equation, and because we can see the graph, we know there's no issue at that x value. We either plug it in, algebraically get 5, or we look at the picture and go up and see it hits 5. Okay. Now on the back. The intention here was for us to take all of these numbers, some of them hideous, and plug them into this. I'm going to assume that every one of you knows how to operate a calculator. I'm not using my calculator. I'm just going to show you what the numbers would have been had you plugged them in. I mean, you literally would have done negative 500 plus 3 times negative 500 minus 4. Like, you just would have done the math. I'm just going to save us the trouble, and I'm going to write down what those values are. Is everybody okay with that idea?
Yes.
There's no math trickery here. There's nothing missing out on a calculator. It's just you're not having to watch me plug numbers in. Okay. Here's what we would get. 0.998, 0.99. Negative 999. That was such a big jump because I went from 2 to 100 and from 100 to 500. Because we were letting the x values get really big this way. That's why. Now, if you attempt to plug in negative 2, it makes the denominator equal 0. That means the graph doesn't exist there. Anybody want to take a stab at what D and E stands for?
Does not exist.
Does not exist. Yes?
Why does it not exist?
Because that puts a 0 right here.
Oh,
You can't divide by 0. So anytime you attempt to divide by 0, does not exist. It's like saying undefined.
oh,
Because it would make the bottom equal 0. Cooper?
Is there going to be like a question like this?
I don't know. Maybe. There might be. Okay. Now, if you plug in negative 1.999, you get the number 1001. Plug in 0. Life is good at 0. 1.5. 3.999. 1.167, which is rounded. Okay? Try to plug in 4. 0 in the bottom again. 0 in the bottom again. Undefined. graph does not exist. But if you plug in 4.001, you will have to round, but you get this number. How about that? Interesting. Yes?
Does that mean it's not function, or is that?
No, it just means the graph has a problem at this number. Like a vertical asymptote or a hole in the graph.
I meant like no, the y. Oh,
Yeah, I'm just rounding. This is actually 1.1. It's attempting to be 1.16 and the 6 repeats forever. That's what it's attempting to be. Plug in the number 100, you get 1.01. And plug in the number 500, you get 1.002. And now we get to answer a bunch of questions about this. Now here's what we're going to do. For you, it's not quite as impressive, but for the video and for what you could see on my screen, all I have is a table of data. So we are now going to answer the rest of these questions with only the table of data to go by. Sounds a lot like some of the test questions that you've been dealing with, I hope. Did he just take my marker? What?
I don't think you meant to. I think you did. You also scribbled his name. That's not a name, that's a scribble.
Jesus.
Is he gonna snap highlighters in the bathroom?
It's not a highlighter, it's a dry erase marker. They don't smell very good. Unless he plans on writing on the walls or something in the bathroom.
He might.
He might. All right, well. It's on video. It's on video. So if there's a vandalism report, we all know that it was Sage Belair. He had to go poop and scribble on a wall. Okay, well, anyway. I hope he watches this video so he can hear that. He's the class president? Oh my God. Oh, Jesus. Okay. Oh my God. Okay. But anyway, we got here. Okay, back to the math. Anyway, we're going to solve the rest of this question with no knowledge of the equation that's up above this table. All right? Check it out. Look what's happening. As x got closer to negative 500, look what these numbers were heading towards. They were heading towards 1. And look what the numbers were heading towards as x got closer to the number positive 500. 1 again. So as x got really, really big to the left, and as x got really, really big to the right, I approached the same y value. So what does that tell us? It's the horizontal asymptote. Because that's the end behavior. It's describing your y values approaching an actual value as x goes really far left or really far right. That's the definition of a horizontal asymptote. No, you have to assume that the behavior you're seeing is... You don't... Look, if you hear hoofs, I don't want you to think, I wonder if that's a zebra. If you hear hoofs, your immediate thought is, that's probably a horse. Okay? Okay? That's how that works. Anyway. Now, let's go to x equals negative 2. This says go immediately to the left of x equals negative 2. Look at this y value. What was it what was it doing? Well, you're pointing down with your hand. What points? Negative infinity. There we go. It's screaming down to negative infinity. But look at the number directly to the right of negative 2. That's a big number, a big positive number. Infinity. No, our graph is approaching the infinities at that x value. So what does that tell us? Vertical asymptote. Because your graph will always go to an infinity at a vertical asymptote. Oh, he's back. Let's see if he brought back my marker. Where's my marker, you thief? Oh, he has it in his hand still.
I'm sorry, I accidentally took it.
That's okay. Hey, you should watch today's video to see what you missed.
What did I miss?
Oh, you're going to have to watch it to find out. Yeah, buddy.
Should I like wash it?
Oh, where did you put the marker that you need to wash it? Jesus.
I'm just like,
Just, you know what? Why don't you just keep the marker? I'll just get a new one.
for real?
No, I'm not serious. I'm going to make everybody else use your poop marker. All right.
No, bro, I did not on the marker. Where would that marker go?
As x approaches 4, check this out. Look here. Both sides. As x approaches 4, the y values were not supposed to be able to see the equation. Your y values were approaching what would have looked like 1.16 repeating on both sides. And 1.16 repeating, I happen to be a big nerd, I know is 17 over 16. It's 1 in 1/16. Oh, wait. No, wait. Maybe I'm not as big a nerd as I thought. Poop! Shh. Now I think it's 7 over 6. Out of nowhere, I think it's 7 over 6. London. See? I told you. Thanks, London. 7 over 6, not 17 over 16. I'll be okay. Completely thought that up on my own, too. No help from the crowd. 7 over 6. Now, wait a second. My y value at the number 4, at the number x equals 4, did not exist. However, the limit at that number was the same value on either side. So what does that tell me? There's a hole there. Specifically 4, 7 over 6. Because we knew it didn't exist at 4. But, wait, what's he doing? Wait, what's happening?
What?
Wait, don't put the poop marker over there. Now I got to use it.
I got a different one.
Oh, okay. Okay, anyway. I'm gonna go find myself a brown marker and put it over there. All right, g of x has a hole at 4, 7 over 6. What do we know? Now, just from this table. Oh my God, I didn't even think about that. He says you're not going to get reelected. Oh God. I do now. They told me while you were gone. Okay. Oh God. This marker's a smoking gun. Okay. Look. What do we know about g of x? What do we know about... What does it say? What do we know about the g of 0? That's stupid. What do we know about g of x because of what we see here? What is that? So if I have a y value there, what does that tell you?
It's real.
It's a real point. And London, what did you say? That's the y-intercept. Because when x is 0, you're on your y-intercept. So not only, because there was an actual y value there, we know the graph exists there. But more specifically, that's our y-intercept. It says find the real zeros of the function by simplifying the expression. Oh, now we're allowed to look all the way back to the top. Hey, look, there's an expression up here. It says simplify it. It simplifies to this. Obviously, it doesn't exist at x equals 4 still, but where are its zeros if there's more than 1? At x equals -3. Yep, because that's what makes the numerator equal 0. And then it says, using the table and this result, state the intervals where I'm above 0. So I'll tell you what I'm going to do. I know there's only one x-intercept. There's only one. And I know there's two x values where it's undefined. remember, on sign diagrams, we use zeros and points of discontinuity, places where it's undefined. So we're going to have -2 on there. We're going to have, -3 on there, -2 on there, and 4 on there. -3, -2, +4, picture not drawn to scale. And now we're going to use our table to decide positive or negative. So look up to the table and find a number that is to the left of -3. There's one. What do we know about our y values? They're positive. Good. Now look between -2 and -3. I only see one number between -2 and -3. It's this one. And it's negative there. Find a number between -2 and 4. Both of these, you can't see, both of these work, and it's positive. And then find a number to the right of 4. They're all positive y values. So where is g of x greater than 0? Everywhere I put a blue plus sign. I'll just write it over here. It's greater than 0 from -infinity up to -3, and also from -2 to 4, and also from 4 to infinity. I have to hop over 4 because at 4 my graph does not exist. Where is it less than 0? That's where it's negative, from -3 to -2. Just like that. And that's all. And most of that, other than this right here, was done from a table of values. I know that I told you those values, but if you had the values, would you be able to use this kind of logic to tell you what's going on with the graph? If the answer is yes, then I'd say that this was a successful mission. Thank you, nerds.